Polynomial functions of higher degree. Polynomial functions have very predictable shapes. All cubic functions will have two bends in them. If we have a cubic function that the leading term is a positive number, bigger than 0, we're going to have a cubic function going from the lower left up to the upper right. Lower left, upper right. And it's going to have two bends in it. And they can be very deep bends or just very minor bends, like those. And the same thing if we have it, the leading term is a negative number, then we're going to be starting at the upper left and going left to right, going down, but we're still going to have two bends in our function. Similarly, quartic functions, the polynomial to the fourth will have three bends in it. 1, 2, 3. This one has three, but they're very, very slight. And if that was on our calculator, we could zoom in to see that. So here we have on these two, our leading term is positive, and here our leading term is negative. So these are quartic functions. Here's a theorem for you about local extrema and zeros of polynomial functions. A polynomial function of degree n has at most n-1 local extrema and at most n zeros. So what does that mean? How are the local extrema represented? On a graph, local extrema are going to be the bends in the graph. So if we have, looking back at the last, we have a function of degree n that will have at most n-1 local extrema. So a function of degree 3, for example, will have at most 2 local extrema. There's our third degree. If we have degree 4, we'll have at most 3 local extrema. And there's a fourth degree. So that takes care of how they're represented. They are the bends, and that is showing you what the graph looks like. And then the third one is, what does it mean to have a zero? Because in the slide we said that it had at most n zeros. To have a zero means it crosses the x-axis. Let's start off with the leading term test for polynomial end behavior. What this means is that we can tell by the leading term, which is the first term in a polynomial, what the end behavior is going to be. The end behavior would be the ends of the lines. So if we have our polynomial where the leading term is a positive number and the exponent is odd, we're going to have our graph going off in opposite directions, positive infinity and negative infinity. If our leading term is a negative number, then we're starting at positive infinity and going toward negative infinity, left to right. If we have an even exponent, then the ends of our graphs will be going in the same direction. So if our leading term is positive, both ends will be going up to positive infinity, and if our leading term is negative, both ends will be going to negative infinity. So applying this to describe the end behavior of g of x equals 2x to the fourth minus 3x to the third plus x minus 1, because it is a positive coefficient on the leading coefficient, and an even number on the exponent, then the limit as x approaches both positive and negative infinity of g of x, both of these will be going in the positive direction. So we'll have our graph will have some bends in there because it's a fourth degree, and both of them will be heading off into the positive direction. Try this one. Describe the end behavior of f of x equals negative 7x to the third plus 2x squared minus 14x using the limit notation. Zeros of a polynomial function. Finding the real number zeros of a function is the same thing as finding the x-intercepts of the graph. We want to find where f of x is equal to 0, and factoring a polynomial will make that easier. Finding the zeros of a polynomial function. To find the zeros, the first thing we want to do is to factor it, and from this function here, we can factor out 2x, and that leaves us with x squared minus 2x minus 3, and then we can factor that into two binomials, x and x, looking for factors of 3 that subtract to give 2, which would be 3 and 1, and the larger number is negative. So we factor that. To find the zeros, we set it equal to 0. So then we know that either 2x equals 0, x minus 3 is equal to 0, or x plus 1 is equal to 0. So our three zeros are x equals 0, x equals 3, and x equals negative 1. And those will be the three spots that it crosses the x-axis. And to support this graphically, if we put this same function into our calculator and graph it, we can see that it's hitting it at 0, at negative 1, and 1, 2, and 3. Try this. Find the zeros of this function algebraically, then check it on your calculator and support it graphically. Multiplicity of a zero of a polynomial function. That's another good word there. Multiplicity. What it means is that if f is a polynomial function and x minus c to the m is a factor of m, but x minus c to the m plus 1 is not, then c is a zero of multiplicity m of f. That really didn't explain what it was. That's more of the theorem. Now let's look at what it means. Let's take this polynomial that's been factored. F of x equals x minus 2 to the third times x plus 1 squared. We say that this polynomial function has a repeated 0. It has two repeated zeros because this 0 repeats and this 0 repeats. So if we solve that, we'd have x minus 2 is equal to 0, so x equals 2, and that is repeated 3 times. And the same thing, x plus 1 equals 0, so x equals negative 1. That negative 1 is a 0 of multiplicity 2. Once we know the zeros and we know whether they're odd or even multiplicity, we can use that to determine what the graph looks like. So if it has a 0 of odd multiplicity, then it crosses the x-axis and it changes sign at x equals c. If it has a real 0 of even multiplicity, then it does not cross the x-axis and does not change sign. Let me show you what that means. even multiplicity 0 makes the graph barely touch the x-axis and turns it back around the way it came. An odd multiplicity 0 crosses the x-axis at that point. So let's use this information to sketch a graph. We're going to sketch the graph of f of x equals x plus 2 to the third times x minus 2 squared. We want to consider the degree of the polynomial, the end behavior, the zeros, and the y-intercept. The degree of this polynomial is going to be 3 plus 2 is 5. So our degree is 5, which means it's odd, so our ends are going to be going opposite directions. If we look at the leading coefficient is going to be 1, and it's positive, so that means we are going to be going from the negative to the positive. So that takes care of the degree and the end behavior. The zeros will be at x equals negative 2 and x equals positive 1. X equals negative 2 is a 0 of odd multiplicity. That means that it will cross the axis at that point. And x equals 1 is of even multiplicity, so it will not cross the axis at that point. It will come down and just touch it. Then we want to figure out where the y-intercept is. So the y-intercept is x equals 0. So we'll put 0 in. We'll have 0 plus 2 cubed times 0 minus 1 squared. So 2 cubed is 8 times negative 1 squared. 8 times 1 is 8. So at 8, we'll just say that's 8. We'll label that 0, 8. 8 is where it crosses the y-axis, and that's a very rough graph of that function. But it tells you the zeros, it tells you the end behavior, and it tells you the y-intercept. Try this one. Sketch the graph of f of x equals negative x to the third times x minus 2 squared. Consider the end behavior, the zeros, the multiplicity, and the y-intercept. When you've made a rough sketch, check it on your calculator. One more thing, we can work backwards. If we're going to find a cubic function with a given zeros, we can make our equation to be x plus 2, x minus 3, x plus 5 is equal to 0. This is a cubic function. When we graph it out, all of these would be our zeros. Put it on your calculator and try it. And now, just for fun, is this a shirt of a polynomial? See you in class.